In this video, we're going to switch gears and we're going to talk about something completely different. We're going to talk about what we call sequences. And this is where we're basically dealing with patterns of numbers. So it's just strict patterns with dealing with numbers. And so a sequence is an ordered list of numbers. One of the most well known sequences that we use very often is your set of all real natural numbers, right? There you create a sequence, right? Your set of all natural numbers. For instance, your natural numbers, those are your counting numbers. So when you're a kid and you first start learning how to count, you usually start at one and you go to two to the next integer up to three, four, five, six, and you can go on forever and ever and ever and ever. And those numbers are what we call the natural numbers, right? And so that's a sequence of numbers because there's a natural ordering or there's a pattern that helps you get from one number to the next. You add one unit. And so we can write sequences in different ways. We can take different subsets of certain sequences and come up with more sequences. For instance, we're going to write the numbers that are associated with the following sequences. Your even natural numbers. Remember, your even natural numbers are your numbers that are divisible by two, right? So that's the lowest one is two, then four, then six, then eight, then 10. 12, and we can go on forever and ever and ever and ever. I guess I only needed three of those. But that's your set of even numbers, right? Even natural numbers. And again, it is a sequence because it is a pattern. You add two to the next to get to the next number. Another one is that another example of a sequence is your odd natural numbers that are less than 10. Well, my first odd natural number is a number that's not divisible by two, is one, and then I add two to that to get to my other natural numbers that are odd and less than 10, 3, 5, 7, 9. If I added two to that, I will go beyond 10. And so this is my set of odd natural numbers that's less than 10. It constitutes a sequence. Notice here, this one continued. I guess I should get rid of these extra things here. This one continues forever and ever, and this one stops at 9, right? And so the difference between these two sequences is that one is infinite and the other is not infinite, it's finite, right? And so we're going to define infinite and finite sequences. An infinite sequence is a function. We've heard this word before. A function is a relation between two sets of numbers. We're going to do two sets of numbers such that each input corresponds to one output, right? And so an infinite sequence is a function whose domain is the set of all positive integers. So positive integers are exactly the same thing as saying natural numbers. All right. And so since we have our sequences defined as a function, that means we have inputs, which represent our domain, and do we have outputs, right? So we have our inputs and our outputs, right? And so if our inputs, and if the sequence is the set of all positive integers, my first integer is 1, my second integer is 2, my third positive integer is 3, 4, 5, and so on and so forth, right? Since we said that part A in this example one was an infinite series, infinite sequence, let's go ahead and write this, our set of all even numbers. Let's do this in this context here, right? So we're going to do this in the context of all of our even numbers, right? Because they constitute an infinite sequence. Well, if my inputs are my all positive integers, then I can think of my outputs as being the actual values that are in my sequence, right? So it inputs 1 into your sequence and your output is 2. You input 2 into your sequence of even natural numbers and your output is your second value, which is 4. You input 3 into your sequence and your output is your third value. So basically the input tells you the location or which element of your sequence you have, right? Your first element is your first element. So your inputs are your location, or is identifying the actual location or which element you're talking about. That's the inputs. and your outputs are actually the values that make up your sequence. So these are the values of the sequence. And I'm going to say this is the position. Which one, right? And so we can do a similar thing with the odd integers that are less than 10, right? It is finite. All right. And so the finite sequence is a function whose domain is the integers. Uh-oh. Hold on one second. Function whose domain is basically your natural numbers that are less than or equal to some value, right? So it's going to be your positive integers are your natural numbers up until you get to the last number in your sequence, that position of the last number in your sequence, which we'll usually denote by n. All right, we can say that it's the positive integers less than or equal to a fixed positive integer n. And so if we look at the odd integers less than 10, again, our input gives the position, or it tells you which integer, which position or number in your sequence you're going to have, right? And so our outputs are the actual values that are in the sequence. So that's 1, 3, 5, 7, and 9. So you input 1 and you get your first element in your sequence. You input 2, you get your second element in your sequence. You input 3, you get your third element in your sequence. You input 4, you get your fourth element of your sequence. And you input 5, you get your fifth element of your sequence, right? And so here our n equals 5, all right? But that's the one way to think about your finite and infinite sequences. They're functions whose domain are your positive integers, and those positive integers basically tell you which position you're looking at, all right? The actual values in the sequence are called terms, and A sub n is a formula for your general term in a sequence. For instance, I can give you a formula instead of listing the numbers out like here, this, or saying it in words. Sometimes we want to give a formula for your sequence, right? For the terms in your sequence, the actual values in your sequence. And so this A sub n is what I'm calling the general term, or the formula that represents that sequence, right? So since we're given this, we can actually use it to help us come out with the numbers that are in our sequence, right? So it says find the first 3 terms of your sequence. Well, what I'm going to do is I'm going to remember that my sequences are like a function. I input my positive integers, right? So my first input is going to be n equals 1. So I'm going to have a sub n. So I'm going to replace this n with a 1. And wherever I see a 1 on the right-hand side of this general term, I'm going to replace it with a 1 because that's going to give me my first term, because that first term is my first position, right? My element in my term in my first position. So a sub 1 equals, that's negative 1 to the 1, which is negative 1. And then 3 to the, 1 minus 1 is 0, and 3 to the 0 is 1. So a sub 1 equals negative 1. I want the first 3 terms, so I'm going to find a sub 2. That means I'm going to go back to my general term. Everywhere I see an n, I'm going to replace it with the 2. So I'm going to put a 2 there, and that's going to be the 2 minus 1. Negative 1 squared is a positive 1. And then that'll be 3 to the first power, or 3. And so this equals 3. And then I get a sub 3, and I have a negative 1 to the third power times 3 to the 3 minus 1. And that'll be a negative 1 times 9, which is a negative 9, right? Notice here, there's a couple things that I want you to notice here, right? This negative 1 to the nth power, right? Because our n is always going to be an integer, and integers can be either even or odd. Notice this creates a negative, positive, negative swapping of the signs of our values, right? I'm going to do one more. I know they didn't ask us to do that, right? But we can kind of go ahead and tell that this next term is going to be positive. That allows us to alternate by having negative 1 to a power. It allows us to alternate between two values, positive and negative values, right? Negative 1 to the fourth power is a positive 1, and I multiply that by 3 to the third power, which is 27, and I get a positive 27, right? So these are powers of 3, and basically I'm alternating them between positive and negative values. 3 to the 0, basically, 3 to the first, 3 to the second, 3 to the third power, and it's alternating negatively, right? We never had a function when we were dealing with functions that had a negative to an exponent, a negative number to an exponent. And the reason for that is because it creates a function that is not continuous, but they do show up here when we talk about sequences. And so if I want that alternating behavior, I need to have that negative 1 to some power. Now, sometimes we can adjust this so that negative 1, so that our first term is not a negative, right? So since our first term is 1, when I plug in 1 here for n, I'm going to have negative 1 to the first power, which is negative. Sometimes we can make this a negative 1 to the n plus 1, right? And then that way, when we plug in 1, when we plug in n equals 1, we get negative 1 to the 1 plus 1, which is negative 1 squared, which is a positive 1. So if I wanted to start out being positive, I can make that exponent on the negative 1 n plus 1. But if I wanted to start out being negative, I can just have that exponent being n here. All right. There's some other cool things that happen with these sequences here. There's another notation called factorial notation. And this means for any positive integer n factorial just means to multiply n. Now, this is an integer, a positive integer. N factorial means to take that n and multiply it by all the other positive integers that are less than it, right? So if I start at n, the next positive integer that's less than n is n minus 1. The next positive integer that's less than n is n minus 2. And I'll continue this until I multiply by 3. The next positive integer less than that is 2. The next positive integer that's less than that is 1, right? So this is what this symbol means. It's saying do this multiplication. For instance, if I have 5 factorial, for instance, this means to multiply 5 by 4, multiply that by 3, multiply that by 2, and multiply that by 1. And then that's going to be what 5 factorial equals. 5 times 4 is 20, times 3 is 60, times 2 is 120, times 1 is still 120. So 5 factorial is the same thing as 120. So instead of writing all of this multiplication out here, we like to use this symbol here, and that's called factorial notation. It's used in combinatorics and permutations in statistics and probability, but it does show up in sequences and series. And so let's look at this one. We're going to find all terms of the sequence a sub n equals n plus 1 over n factorial for 1 less than or equal to n less than or equal to 5, right? And so what we're going to do here is we're going to start with n equals 1. So we're saying that our n, which is always going to be a positive integer for us, we're going to start at n equals 1, and we're going to go all the way through until we get to n equals 5. And so first, we're going to find a sub 1, which is our first term. We plug in 1 wherever we see an n, so that'll be a 1 plus 1 over 1 factorial. Well, that's 2 over, that's 2 over 1. 1 factorial is 1, and so we get 2. So that's our first term. Let's do a sub 2. I'm going to plug in 2 wherever I see the n. That's going to be 3 over 2 times 1, which is 3 halves. Let's do a sub 3. Plug in 3 wherever I see an n. That's going to be a 4 over 3 times 2 times 1, right? That'll be 4 over 6, and we can simplify that to 2/3. All right, we have a couple more. Let's find a sub 4. That's 4 plus 1 over 4 factorial. Well, that'll be 5 over 4 times 3 times 2 times 1, right? And so that'll be a 5 in our numerator. 4 times 3 is 12, times 2 is 24, times 1 is still 24. So the third term in our series is 5 over 24. And last but not least, we'll have a sub 5. We're going to plug in 5 wherever we see an n. That's going to be a 6 over 5 factorial. We just found that 5 factorial is the same thing as 120. And so that's 120. And so 6 over 120 is 1 over 20. All right. So one of the things that's hard about this, right? So if I were to give you this list of numbers here, two, okay, let's write it here. Two, three halves, two thirds, 5/24, and 1/20, it would be mighty hard to figure out what this original sequence was, right? As you go through more math, you will learn techniques that allow you to do that. All right. Now, certain series and sequences have patterns that allow you to see that. We're going to look at some coming up with formulas when we're given a list like this and coming up with the formula that is attached to that. But we're going to look at some simple formulas. All right. For instance, let's look at this example here. It says write a formula for the general term. Remember, we said that the general term was that a sub n, right? It was that formula that we would give. All right, it's that a sub n. We want to come up with a sub n that represents this sequence. All right, our first sequence is 1, and then we got -1/8. Then we have a +1/27. Then we have a -1/64. So this is where it gets hard, right? We have to kind of look at, what's happening here, right? So remember, our sequences are functions, right? We plug in n equals 1, we get an output of 1 because that's our first element in our sequence. When n equals 2, we get -1/8. When n equals 3, we get 1/27, and when n equals 4, we get -1/64. Well, notice here that there's an alternating pattern between positive and negative. As I've stated above in that previous example, right? Notice I'm going to have a -1 to a power. If my first element in that sequence is -1, it can look like this, right? I have -1 to the nth power. But if I don't want my first element to be negative, as I said before, I could write this as n plus 1. I will also tell you that -1 to the n minus 1 also works, because if I plug in 1 for n, I'm going to get 1 minus 1, which is 0, and -1 to the 0th power is still a +1. And so I'll start with that +1. All right. So I know that my a sub n, since I started with a positive, I'm going to write that as a -1 to the n plus 1 power, right? But I've got to try to figure out what the pattern here is with these numbers here. What I'm going to do is, since all of these have a fraction, I'm going to write this as a fraction as well. So we've already taken care of that -1, that alternating negative, right? Negative, positive, negative, positive, negative. Now I'm going to try to look at these numbers. What do 8, 27, and 64 have in common? Well, if you remember when you're dealing with radicals, these are all perfect cubes, right? That 8 is the same thing. Okay, these are commas in between these. It's the same thing as 2 cubed. That 27 is the same thing as 3 cubed. That 64 is the same thing as 4 cubed, right? And notice here, I plug in n equals 4, and I got 4 cubed in the denominator. Plug in n equals 3, I got 3 cubed in the denominator. Plug in n equals 2, I got 2 cubed in the denominator. And I plug in 1, oh, I can think of this as a 1 cubed. So it looks like I'm raising whatever n I have up here, which notates the position, to the third power. And so my general term is going to be, it can be written this way: -1 to the n plus 1 times 1 over n to the third power, or I can write that as -1 to the n plus 1 over n to the third power. Because if I think of that as being over 1, since -1 is a whole number, we can do that. Then I can multiply across the top, and I'll have this general term here. Okay, again, we can write that. Okay, it just did that. Okay, well, we're going to redo it all. As an n minus 1 instead of an n plus 2 there. All right, let's go to part B here. I have 14, 16, 18, 20. Oh, these are my even numbers, right? Because, and I know these are even numbers because they're divisible by 2. And if you notice here, of course, if we have even numbers, we're going at adding 2 each time, right? So this is like a linear function, to be honest with you, right? With a slope of 2. And so what I could do is I could write my general term, I'm going to switch the color here, as let's say a sub n equals, okay, maybe not. Yeah. A sub n equals, well, if I know I'm adding 2 each time, right? But I'm starting at 14. So what I'm going to do when n equals 1, right? I plug in n equals 1, I get 14. So if I start at 14, I kind of have to wait to n equals 2 to add 2, right? So when n equals 1, I don't want to necessarily add 2, right? So what I'm going to do is I'm going to multiply by n minus 1, right? And this can offset the fact that I'm not adding 2 to get to my first one, right? My first term here, right? When I plug in 14, I need to get 14, but I need to plug in 1. I'm not plugging in 0, I'm plugging in 1. And so in order for me to plug in 1 and not add 2, I need an n minus 1 here, right? So that'll be a 1 minus 1, which is 0. So when I do my a sub 1, I get 14 plus 2 times 1 minus 1. That's 0, and so I get the 14 there. When I do a sub 2, now I want to add 2 to that 14 in order for me to get to the 16, right? So that's going to be a 14 plus 2. My n is 2. And now you see that I have 2 minus 1. So I'm adding just 2 to that, which will give me that 16. And it'll work for that moving forward, okay? Now I'm going to erase this so that I can have some space. But basically what I have here is my nth term, my general term. It can be written like this, or we can use our distributive property. And then we can combine like terms, and we get 2n plus 12, right? And that is our sequence, right? You could actually think of this as coming up with the equation of a line, right? Where my first, remember these are functions, right? Where my point of my line, it goes through, my first point is you input 14, you input 1, you get 14. You input 2, you get 16, right? That gives me a slope of 2, right? So if I used my slope intercept form of my equation of my line, we'll have y equals mx plus b. And so I'm going to use one of these points for y and x. So that means 14 equals m, which is 2, x, which is 1, plus b. That means b, 2 times 1 is 2. Subtract that from both sides. I get 12. And so we get y equals my slope, which is 2. Remember, you can do the change in y over the change in x. That'll be a 2 over 1, which is 2. So that's why I have that m equals 2. And so I have 2x plus b. So that means a sub n equals 2n plus, and not b. Instead of writing b, we're going to actually write what b equals, which is 12. All right, so there's a connection between linear functions in this, because this sequence here goes up by the same number of units each time. And so you can use this method to come up with the equation, the general term, which is this here, or you can kind of figure it out by looking at this and trying to adjust your n so that when you start at n equals 1, you don't necessarily add that slope or that difference between your two values, but you go from there, right? Sequences like this that go up, and this also works if it goes down, right? There's basically a linear relationship between the inputs and outputs. Those types of series are called arithmetic sequences. All right, arithmetic sequences, right? It's a sequence that has the nth term of the form a sub n equals a sub 1 plus n minus 1 times d, where a sub 1 and d are real numbers, right? So this a sub 1 is your first term, and then that d is your distance or your difference between terms, all right? And so if I were to look at that sequence that I just had up there, right, an arithmetic sequence always increases by the same value or decreases by the same value. So this is an arithmetic sequence, right? The A1 is the first term of your sequence, which is this 14. And then the D here is the amount or the difference between your successive term and your previous term, right? So if I do 16 minus 14, I get 2. That means D equals 2. And you can see it. Actually, you can see it right here. This is my A sub 1. This is my D. And of course, I have my N minus 1 there. All right. And so for every arithmetic sequence, we can do that. If it's not an arithmetic sequence, we can't use this formula to find the actual sequence, right? So in this example, we're going to determine whether each sequence is arithmetic. If it is, then write a general formula for it, right? And so I'm going to look at these numbers here, negative 3, 3, 9, and 15. Negative 3, 3, 9, and 15. Notice here, for me to go from here to here, I have to add 6 units, right? I'll do 3 minus negative 3, which is a 6. 9 minus 3 is a positive 6. 15 minus 9 is a positive 6, right? So yes, this is an arithmetic sequence, right? So since it is an arithmetic sequence, right, I can actually use that formula to help me figure it out, right? It's going to be my first term plus n minus 1 times the difference between your successive terms, right? Now, this n always stays in the formula. Since my first term is negative 3, I have a negative 3 here. And my d here is that difference between your successive terms, which is a 6. We can multiply that out. We're going to get a sub n equals negative 3 plus 6n minus 6. And if you wanted to write your term with the n in the first, that would be a 6n minus 9. And so this would be our general term, right? And you can always check yourself by plugging in n equals 1, right? N equals 1, I get 6 times 1 minus 3, that's negative 3, 6 minus 3. N equals 2, I get 12 minus 9, which is 3. N equals 3, I get 18 minus 9, which is 9. N equals 4, I get 24 minus 9, which is 15, right? And so that checks out. Let's go to part B here, right? Negative 4 minus negative 7, that means plus 7, right? Negative 4 plus 7 is a positive 3, so I'm adding 3 to get to that next term. Negative 2 minus a negative 4, that's negative 2 plus 4, that's a plus 2. All right, since these numbers aren't the same, I already know that is not an arithmetic sequence. All right, this stuff is related to calculus 2. And so if you go on to take more calculus classes, you will look at some of these sequences here but for right now, we're just going to get an introduction to that. And we're going to use that in the next video. See you next time.